Tomasz Rutkowski. I am from the RIKEN Advanced Intelligence Project in Japan. Originally, I'm from Poland. And also, I have second position at the University of Tokyo. And today, we have beautiful panel, AI, BMI, BCI, VR and AR technologies in day-to-day and the healthcare applications, as well what is real and what is not. So I would like to introduce my panelists, but maybe they will be like, making slight introduction one by one. So we have Professor Lotte, we have Dr. Yannick, Professor Miller, we have Professor Ball, we have Professor Zander, and Professor, my gosh, Nikulin. Okay, so could you make one by one a very short introduction? And also if you could make some reference to the title, if you are BCI guy, AI guy, and so on. Let's start from the other side.
So I'm interested in neurotechnology, but that's of course not the only thing. I'm interested in application of neurotechnology to clinical environment, specifically for neurology. So my main interest there is stroke and Parkinson research. So in stroke, of course, this is the use of virtual reality for rehabilitation purposes, for establishing an efficient motor control. And in Parkinson disease, I'm interested in applications of neurofeedback for deep brain structures, so that probably you can get away from actually stimulating STN, or you can use a smaller stimulation with a, let it put it this way, less aggressive ways. And of course, in general, I'm interested in developing neurotechnology in the context of brain-computer interface and neurofeedback.
Yes, my name is Thorsten Zander, and I'm from Berlin. And I personally work on brain-computer interfaces in general, but mainly on the application in the field of human-computer interaction. So how can we make our daily interaction more powerful, more secure, more interesting to people by implementing input from the brain to the machine? And there I see the great benefit not only in direct control, that you replace a mouse or a keyboard, but that the machine automatically adapts to its user, that the machine gains some kind of empathy, understanding to its user. And then one step further, where I'm currently working on, is something I call new adaptivity, so that the system adapts automatically to the user in a more powerful way by using artificial intelligence. And from that perspective, I work on the convergence of human and artificial intelligence, so that we bring AI and our own intelligence closer together by this link we have now available, which we call brain-computer interfaces. And from that perspective, I also have a clear ethical perspective that I see that we have to deal with this new kind of technology which will come. It's not future, it's no dream. It is there now. Big companies will work on that. And I think we should be aware and have some means to deal with that when this appears. So I'm focusing currently very much also on ethical considerations.
Thanks. So, yeah, my name is Tonio Ball, and I'm affiliated with the Department of Neurosurgery at the University of Freiburg in Germany. And also from my background, I'm initially a clinician, but now working in research full-time. And I guess I'm interested in all the topics that were just mentioned, especially what I like to do is work very closely together with colleagues from the technical faculty and so to do some kind of translational neurotechnology research. And this was also like the old name of the lab, but then the abbreviation of that is TNT, and this people thought this sounds too aggressive, so we renamed ourselves. But this is actually what I'm interested in, doing kind of preclinical translation of new technical developments into the clinical field.
My name is Lee Miller. I'm at Northwestern University in Chicago, and I'm affiliated with the Physiology Department, Department of Physical Medicine and Rehabilitation, and Biomedical Engineering. And for the most part, I have studied the basic sciences of the sensory motor system, particularly during reaching and grasping, but in the last 15 years, I've gotten involved in brain-computer interfaces. The main application being to spinal cord injury, and sort of take the opposite approach. Instead of putting as much intelligence in the periphery as we can, I try to make interfaces that are as biomimetic as we can, that allow the brain to connect to our computer in a way that preserves the natural function in the brain to the extent that we can. I'm also the president of the Society for the Neural Control of Movement. We're having a meeting in Croatia in April, and I would welcome any of you to consider attending and submitting proposals for workshops there.
Hi, I'm Yannick Roy. I'm from Montreal. I'm probably an imposter here since I'm not a doctor. Still stretching my PhD for a couple of years because I'm a neurotech enthusiast. I'm passionate about different things in neurotechnology, namely about closed-loop systems, so passive and reactive BCI, namely, and VR, among other things. My PhD is on cognitive training with closed-loop system. I'm also co-founder of NeurotechX, which is an international community of neurotechnology. We do a lot of events, workshops. We have student clubs, chapters in different cities around the world. So that keeps me a little busy and not finishing my PhD. But I'm excited to be here. More recently, I was excited being in Montreal by AI. So in Montreal, it's all about deep learning. Being at University of Montreal with Yoshua Bengio, among other people, I segue into AI deep learning for EEG, and we're going to be talking about that this afternoon. So excited to be on the panel and discussing a bit more.
Good morning. So my name is Fabien Lotte. I'm from INRIA, which is a public research institution in France dedicated to computer science and applied mathematics. So I'm myself a computer scientist. And I've been working on BCI for many years now. So initially I was working mostly on the signal processing and machine learning aspects of BCI with application to using BCI to control virtual reality environments and augmented reality systems. And more recently I've been moving on to studying more the human sides of BCI, trying to understand the human factors involved in BCI control, trying to improve the learning, the user training and the user learning. And so I was mostly working for healthy users before, and now I'm also starting some application also for like stroke rehabilitation or assistive technologies. And I think actually machine learning and AI could possibly be used not only for training the machine, but also for training the user. Maybe, we'll see.
Okay, wonderful. So we have very nice list of speakers here. And first thing, let's start from the AI. So we know we are in the AI revolution. Everybody talks about the deep learning. So if you could make a quick comment, are you happy with the current stage of the machine learning? Or what would you need, more at this stage?
So I am happy with that, not fully. So actually I'm supposed to be the bad guy regarding deep learning. So, so actually there's definitely a big revolution for deep learning in many fields. And obviously in BCI there's also a lot, and actually Tonio mentioned a lot of papers on that recently. But I have to mention that so far in BCI, with a few exceptions, and actually the work of Tonio is one of these exceptions, there's a lot of work on deep learning in BCI which does not clearly show the benefit of deep learning for BCI. Because they don't really compare to the state of the art, or the experiments are not too rigorous. So again, I'd like to stress that the work of Tonio is really an exception because it's really clear. They share everything. It's really rigorous, so the benefits are very clear in that case. But it's not always the case in the literature, which is a pity. And so I think what's missing is maybe more rigorous evaluations, sometimes we don't really know where the architecture comes from, whether the architecture has been optimized with the knowledge of the test set or something like that, which might bias the results. And we see that maybe too often in the papers. So maybe better standards of evaluation will really be able to show whether deep learning is really beneficial for BCI. And clearly another big problem is the data problem. So we need usually a lot of data for deep learning techniques. And in BCI, we often don't have a lot of data. So what we are missing is very good algorithms for very little data.
I would definitely echo what Fabien just said. Earlier this year, we published a paper. We reviewed 154 papers in deep learning for EEG. And what we've seen is definitely that first, what Tonio Ball and his group is doing is pretty remarkable. But we definitely have a trend where a lot of people were excited about deep learning. Is it better? And people were publishing pretty much everything on any sort of data using any sort of model, but it's definitely not clear if the results are definitely positive. What we showed is that we have kind of like a median of 5% upgrade versus benchmark. And in most cases, the benchmarks were not really the real state of the art. So people are showing a bit of improvement, probably because of publication bias as well. So obviously, the results shown are positive. Otherwise, they probably wouldn't have been published in the first place. So it's hard to tell if there is a real benefit, but definitely the trend that it shows is that it has potential. So for me, I'm definitely excited about the future of deep learning for EEG, but we need more data. But more than that, we need reproducibility, I think. What we've shown in by reviewing all these papers is that only, I think, 8 papers were reproducible, meaning that they shared the code, they shared the data sets, they shared the parameters, so we could actually reproduce the study. But that's a very, very small percentage, so it's hard to assess if the percentage are really good, actually. A lot of the details in the publications were missing. A lot of the people were coming from EEG machine learning, but they didn't include all the important details that deep learning needs in the publication, so it was really hard to understand if they were doing double dipping. A lot of things are not really understood as well in terms of data augmentation, sliding window when they are putting the input to the neural net. So a lot of things need to be better understood, and I think that reproducibility will help if people share their code, their data sets, and as we have bigger and bigger data sets and better framework like Brain Decode, for example, I think that this will help push the field forward. But I'm definitely excited with the potential. But we're at, because deep learning have shown to be at least as good as benchmark, but is it really better? That's the question that I think hasn't been solved just yet.
I think the advantages of deep learning with respect to natural language processing, image processing are very clear. There are remarkable advances that come every few weeks in the field. As I mentioned yesterday, we have some very recent results now with respect to processing of time series and neural signals that we're excited about pursuing. But I think an interesting question with respect to closed loop BCI is what advantage deep learning may give when the brain is inside that same, when our own brain is inside that same loop. We know it's powerful and adaptive and so forth. And it may well be that we don't need the power of a deep network as if we've got our own network inside our skull processing the same signals.
Yeah. Thanks for also what you just said, and but I couldn't agree more with everything that was said before. Maybe I would even put it a little bit more drastic, because I think right now, from my perspective, it's really not clear at all that there's any reproducible performance advantage, and I think I think it's also understandable if you imagine that a PhD student, for example, has this project with this cool new method, and would of course now, and it's also it takes an effort really to get into that, and then I think it's very natural that you would maybe use 80 or 90% of your time to work on the deep learning part, and then of course you have to do this comparison to a baseline, and then maybe I imagine you would invest 10 or 20% of your time and effort into your comparison, and this is obviously a bias, and I think this is really a problem that is really hard to solve. So what I did is that in my group I have now one really good computer science PhD student, and he's purely working on classical feature-based methods to have this someone who's concentrating on the other side. And yesterday I showed this our study on the pathology decoding, and now he redid this whole feature-based approach, and really spent now, I think, 2 years in optimizing this feature-based pipeline based on our current collection of, I think, 9,000 features, and we tried AutoML, Riemannian decoding, everything, and then at the day of the, and we, of course, this is, I think, a very important point, put aside some data that was not looked at all until the final evaluation. And then there was the great day, and the final result was that all methods were around 85% and statistically not different anymore. So, and I think this now we are just writing up the paper, and now I think I don't see a lot, if any, previous studies that would have really taken such an effort to make a comparison. Even our own, I think we have to redo them. So yeah, long story short, I think I absolutely agree. Right now, it's not clear that it has any performance differences, and I think one likely reason is that just our data sets are probably not one, but more than one order of magnitude too small to really get to that point. But yeah, so I think for me, the major benefit of it all right now is that also the other way around, I think there's no traditional method that would be clearly superior to deep networks. And what we can do with deep networks, also like very nicely in your examples on spiking data, is that, if I got it right, that we can train it on the raw data. And I think this so I see that maybe deep learning for brain signals could take a different course compared to computer vision, where the story was very much driven by performance. So maybe in our area it could be that having a method that works on raw data opens really possibilities for I think to better understand what's informative in your signals, and with our brain data, I think it's a much more important topic to understand the informative features, and maybe this could be more of a driving force to have a setup where we can really see if we understand what's informative in our data. And so this would be right now my take on that. So but I think it's a very dynamic field, and who knows what happens in the future. And I think I'll stop now here. So, but we were supposed to have a fight, right? So now, what do we do now?
I was going to say, as we consider whether deep learning is important, I'm going to make the argument that unless we have high bandwidth, high detailed, invasive kinds of signals, there may be no difference. How's that for controversy?
Okay, I'll think of an answer while.
Okay, so I personally see two ways how we could use machine learning and AI in the BCI field. And the now mainly used version is that we try to improve classification accuracy by using more complex methods. And like we heard before, I fully agree to that's difficult. But there's one thing which is also about the informative features, which I would like to stress out. So when we use any electrical signal, it could be from the brain, it could be from muscles, it could be from eyes, it could be artifacts in it. And basically when we use a BCI, the performance of the BCI is not a good measure whether it really works. And so we need to interpret the features we're using, we need to interpret the methods we use. And so far, it's really difficult also already for the simple methods, the linear methods we use, to understand on what features they work on. It's not enough to see that there's a signal in the brain and that it's working well to know that the BCI really used also that feature in that regard. And I personally, in my research, use the simplest methods that are available, linear discriminant analysis and CSP, which are really on the market for 20 years already in BCI research, and which really work well. And I see a huge benefit to increase classification accuracy or performance by implementing a good calibration paradigm that's much more powerful than having a method that is more complex and maybe gives you 1 or 2% of accuracy. If you design the calibration paradigm in a good way, you might get an increase of 10 or 15% of accuracy because you motivate the participant in a better way, you get the signal out of the brain which you want to get out of it. But like I mentioned before, there's also a second way how we could use AI and machine learning in the field of BCI, and that it's at the end of the pipeline. So we have any kind of BCI giving us information about the human, about the human state, a state change in the human brain. What do we do with that? So currently we steer a cursor to the left or right, but we might also inform an artificial intelligence which learns over time how we see the world, how we interact with the world, and builds a model of our own cognition. And then the BCI is only one additional sensor providing information to that AI. And that's, in my perspective, the much more powerful way how we could use machine learning and AI in correlation to BCI.
I would like to touch another aspect which has not been addressed, and this is educational. So basically, what happens if we start running before we learn walk? So usually we fall. So the point is that I'm working on a few deep learning projects where PhD students come so excited about this technology that they immediately start applying it to the data without knowing even the basics of the process. The danger is they apply it to raw data. So we all know in EEG, MEG that raw data contains everything you can think of, not only brain data, but also different bodily signals. So the problem with this is that they are so excited about this that it's very hard, for instance, for them even to learn the basic, that there are different rhythms, there is a phase of information and so on. So while of course deep learning is very good, so the danger is that unfortunately it's also a kind of a shortcut. So many things, if you would like to do fundamental science and falsifiable hypotheses, they are not easily kind of implementable with deep learning. You can do it, but it's much more complex. So therefore, while I agree that this is a way forward, that we have to be very careful, especially with like master students and PhD students who immediately jump on it, and well, different things can happen. And another aspects we today in the morning were discussing is what is the way you apply deep learning. So if you want to do it in an applied way, for instance, to say that this patient has a certain symptoms and we want to predict it, so that's fine. But if you want to know exactly what is the origin of this, this is another story. Like we were discussing about this nonlinearity, where it appears like before you start doing the mixing of channels or after this. And depending on this, you will have different interpretations. So all of this, of course, is important for fundamental research.
Great, wonderful. The good news is we have a lot of research to do, so we are safe maybe for the next 20 years. If there are any questions from the audience or you have any comments, I would like to engage you as much as possible.
Thank you. I have, well, a question. I have quite a lot of friends who are doing deep learning or who dislike it. And most of the people who dislike deep learning, they're saying something that there are only like two ways you can you're applying it. Either no one has invented like classical model how to do it, and you're just like cheating with deep learning because no one knows how to do it another way, or you are lazy to apply more like difficult classical approach. So the question is, do you think that as like science go forward, things that are now solvable only with deep learning will be like modeled more classical way, so you can have not deep learning but classical model? Or do you think that some tasks will always remain in the domain of deep learning and no classical model can be applied for these tasks?
Any takers? Tonio?
Okay, first of all, I'm sorry to hear that your friends are somehow having a hard time. So I didn't exactly get what their problem was, but yeah, I'm sorry. But the other thing is, I think it depends on how do you define deep learning. So I think in a wider sense, it's not tied to artificial neural networks, but you can also have deep other methods. You can stack other methods, and so I think the basic idea is that you have a hierarchy of representations, and I think this, in some sense, I could imagine that many problems will be somehow very well addressed by such an architecture, and I think it's not a coincidence that our brain apparently does or heavily relies on this principle, and therefore, so in this wider sense, that methods which use like multi-layered representations of the incoming data, I am quite, let's say, positive that this will be something that works better than shallow versions, but well, who knows? And in the more narrow sense, deep learning as we know it today, I think it was a very nice or important point also at our meeting now in Tokyo in one talk, that today's deep learning is really very different from how humans learn. And so we as humans, it's not that as a baby you train classifying 1 million examples of images until you can tell exotic animals apart. So not at all. So human learning is really very different from that. And so I think we still have a long way to go to have something that is really maybe closer to how the human brain learns stuff. And but I think it will be a very interesting journey.
Yeah, I think that for deep learning, one thing is that at the fundamental theoretical level, it can average any function, basically. So the potential that has, I think, is tremendous. Right now, it's all about how we train it and what kind of model that we really don't know. People have been trying CNN, saying that EEG, for example, a lot of spatial features, so that's really important. People have been trying RNN, LSTM because there is a temporal component in it. People were trying in parallel, then in serial, so one after the other. So really don't know how to kind of like best stack the different tools that we have, and also how do you train it, and how much data is enough to be able to train, and how deep can you go. So a lot of the best version right now are working intra-subject and not even between or transfer across subject, but really intra-subject with shallow version. And so is the reason of that because the data itself doesn't contain enough feature, or is it just because the kind of model that we use and the amount of data just doesn't fit together? So we don't really know, and I think that in the future year we'll learn more. And in terms of being lazy when doing deep learning, I don't really agree, but I do agree to the comment that was done with the education aspect of it, because most of the time, when you do deep learning, you'll spend a lot of time not necessarily understanding concepts like that you would do it like as master students or PhD with traditional machine learning, understanding the filtering, the features, the machine learning and the maths behind that. But with deep learning, you'll do a lot of hyperparameter fine tuning, which has no added value from a learning perspective to some extent. But I think that we're going to move forward to AutoML and kind of like more automated. But right now, I think that a lot of time is being spent or wasted as like fine tuning parameters, which has no intellectual value, if I can say.
And otherwise, you ask the question, okay, are there some problems for which deep learning are the best method, and maybe some more traditional method would be better for some other problems? I don't have the answer yet, but what we see now is that deep learning, at least for BCI, is mostly used for classification problems to recognize the mental comments from the users. But actually, there are many other problems for which they could be useful, because deep learning is not just a classifier, it's a kind of generic optimization problem. So now you can see some other application area, for instance, using generative adversarial networks to generate artificial data or to simulate EEG signals, for instance. That could be possibly another application for which it's valuable. It can be also used, there's a recent paper in BCI in which they use that, deep reinforcement learning, to generate automatic sequence of training tasks for the user. So each time you're not optimizing the machine, but you're optimizing the user training, which is maybe also possibly an interesting experiment. So that was only a simulation, so not sure yet it works with a real human in the loop, but that's maybe probably a lot of other problems for which maybe deep learning is more suited than for classification, given the low amount of training data we have, for instance. I don't know, but at least it is worth exploring some other areas.
Okay, thank you. Let's move toward the BCI. Already Tonio brought a very nice subject. We know that current machine learning is using completely different paradigm compared to human learning. So how do you think whether we can use BCI as kind of support for the AI community to introduce better learning strategies? And how do you think who will benefit more, BCI from AI or AI from BCI? If you can make some even random guess.
So I personally think that AI can benefit much better from BCI than the other way around, but I'm biased, of course. And so I think that what I mentioned already earlier, that we can use output from the brain for deep reinforcement learning to reinforce the AI in a context. So we have the human brain, which is trained very well in a context to understand the context. And we have a BCI, which gives an output, which is a summary of all the conclusions drawn or the processes in the brain interpreting the situation. So we could say good or bad. And this is what our brain does in milliseconds and or even shorter. And it does it in a very high accuracy from our own perspective, of course. And when we use that information to feed it into reinforcement learning or deep reinforcement learning, that might be something which is missing in that model. You know, we can use a lot of data to train general processes to understand what people generally like, but what is happening in that moment for that person, in that subjective interpretation, is hard to model generally with big data analysis. And with the BCI, we can provide exactly that information, and that might be the missing piece, which makes the artificial intelligence a little bit more human-like, a little bit more like us. And that's another benefit also from an ethical perspective, I think, that we now are on the verge to creating artificial intelligence, and it could be anything. And so there are different ways to create the intelligence, and when we want to bring in the human factor, the personal idea, the subjective interpretation of the situation, it might lead to more human-like intelligence, or something which we are more compatible to, which we can work better with. And from that perspective, I think it's a broader perspective, of course. It's not going into detail how we classify this or that, but it could be huge benefit for the process we have right now, the development we have right now in artificial intelligence. I don't know if you agree with that, but.
I would add to that I don't think necessarily that BCI per se will help AI, but obviously neuroscience and, well, AI as we know it today is based on the visual cortex mainly, and kind of like different layers and the feed-forward process. But I think that the more we learn about neuroscience, the more we'll help AI and vice versa. But one thing that I'm personally interested to see more in the evolution of deep learning, especially in the training and also the way that the feed-forward process works. We know that in the brain it's more about kind of like top-down, bottom-up, and these loops. But in deep learning right now, we don't necessarily have that concept as much, I feel, as in the brain. So there is kind of like, you kind of like your layer make a decision at time t, whatever, and then the next layer and then the next layer, but you don't necessarily go back in time and reverse that decision to kind of like have an updated, as your brain is giving you kind of like updated very in real time, but we don't necessarily have that in deep learning. So I think that new concept like attention has been added to deep learning recently, and all these kind of like feature from the brain as we try to understand them. So I think that neuroscience is a bit more advanced than deep learning is right now. So we need more of these concepts, or trying to interpret or integrate these concepts in AI right now.
Yeah. Yeah, one, I think, really very interesting development from my perspective is, so you might know, so I think all the big companies like IBM, Intel, and so forth are now very interested in neuromorphic computing, and for example, Intel developed their neuromorphic platform called Loihi, which is really a very sophisticated neuromorphic platform with 128K neurons, which can be configured very flexibly, so you can have synaptic learning rules that you can specify, and so forth. You can define the whole connectivity, and but one big difference compared to the like conventional deep learning networks is that this is really spiking networks. So you have, on the whole chip, there's no clock. Each neuron can spike whenever it wants. So you have a real spiking neural network, and I think from what I understand for Intel, this is now really strategically it's a very important project to maybe get into the edge computing mobile device mainstream with this kind of chip, because it's extremely energy efficient. But now they have the problem that they have a solution, but they don't know the problem they can apply it to, because it's really not clear which kind of algorithm can be implemented on a spiking neural network in a way that it would work better compared to a conventional CPU or GPU solution. And to address this, Intel now created what they call the Intel Neuromorphic Research Community, which is to bring together people from academia and from their side to explore what can be done with this kind of spiking neural networks. And there, within this community, they kind of approached us to make a neuromorphic implementation of our closed-loop deep learning setup to have kind of a neuromorphic BCI. And but mainly, there are many people from computational neuroscience, like really the world-leading, I would say, computational neuroscience people now working together with a company like Intel to figure out what can you practically do with a spiking neural network. And I think this is an amazing development. If you think that it's not so long ago that neuroscience and artificial neural networks, this was like virtually no connection between the worlds, and now these fields converge and really work together. People from machine learning and neuroscience publish together, and I think this is really, I think, could be a game-changing development that these fields really grow together. Now, I'm not really sure for your question if now AI is helping BCI or the other way around, but maybe it's a win-win situation, and I think a really interesting development. I'm very curious where this will lead, and I think it's we live in exciting times.
So maybe we can make a small conclusion. Both fields need each other, and we are lucky to work actually with both. Okay, so let's move. Any question or comment from the audience at this moment? Yes.
Hi, I was actually wondering if you could provide your thoughts on the problem of interoperability of deep learning networks or created models, and maybe from two sides. First, how in many cases of great models created, they were inspired by some a priori knowledge about the system that you're trying to approximate, and the second part on the black box problem of the networks that are being created, and we don't know how exactly they work and what maybe their limits are. What do you think about that?
Well, I think the black box aspect, I think, is really a problem. It's far from being solved. So I think I mentioned yesterday that right now in the deep learning community, there's even if you train like classical networks like VGG on something like MNIST, yeah, it's still VGG is like one of the winner architectures from the ImageNet competition, and is used a lot. And MNIST is this really simple benchmark about classifying handwritten numbers. But even in such simple cases where it's really or classifying simple images. So and even in these cases, it's really an ongoing debate, and there are really surprises coming up when you try to understand what these networks really learn with increasing depth and what they ignore. And I always find it kind of so if you imagine what we try to do or what people try to do in neuroscience. So in this case, we know everything. We know the complete state of the system at each point of time. There's no secret, but still just analyzing it. And I mean, there are really many clever people working on this problem. After now many years, it's still a very open field of research and in neuroscience. So imagine where we sample from like a tiny fraction of neurons, and even with that don't get the complete state of those neurons, how much harder the problem is to reverse engineer the system. So this is kind of surprising, and I think that to really move forward now, coming to your question, I think we need really methods that go beyond the typical mean field approximations. So we really have to develop mathematical tools that can handle these, by definition, and that's what makes them interesting, nonlinear systems in a suitable way. And what we want to do now is team up with people from statistical physics, because there is an interesting mathematical analogy which is already recognized in computational neuroscience, between statistical fluctuations in neural networks and statistical fluctuation in quantum fields. So you can, the only difference or major difference is one is complex values, quantum fields is complex values, the other not. But basically you can apply very deep mathematical tools from the field of statistical physics, like renormalization group, to neural networks. And I think, and there are also other possibilities in this direction. I think, therefore, this is really a really tough problem, in my opinion, and will still take a while to develop even the appropriate tools to address it. But it's definitely not. I don't think that it's somehow black box that cannot be opened at all. And yeah, let's see.
I would like also to be a little bit also more specific and concrete, especially this is to a very large extent the EG community. So we had a very good project with Berlin Brain Computer Interface Group, Benjamin Blankertz, Klaus Robert Müller. So we have, as you know, in BCI a problem of illiterate people. So people who really cannot operate BCI systems. So now the point was we had a very brilliant PhD student who came up with deep learning algorithms which generalized. So finally it's really generalized. So we trained it like on 100 people, and then other 50 people which were not trained, we could actually classify everything quite well. It was astonishing performance. So of course, one of the points is that we were suspicious that it could be due to what? Now, due to eye movements, because they're invariant across many people, and if you use these cursors, you have lots of saccades. But of course, the data was very cleaned. So we cleaned everything using like everything so that there is actually almost nothing. But if you want to generalize, deep learning algorithms are so good that they managed to pull out whatever little things were still lurking there in the shadows. And in the long run, only after very serious scrutiny of this data, we realized it's still eye movements. But this requires actually a massive collaboration between machine learners and neuroscientists, because otherwise you would have problems spotting it. And this is about why it works. Even if you think this could be, well, due to neuronal activity, it still could be something else. And I think this is the most crucial and difficult points in deep learning applications.
Okay, you want to add something?
Yeah, just very quickly before we move on, I think that we need also to understand that we have different ways of using deep learning. So the black box is one thing, trying to understand the feature, but that's one component of deep learning. In BCI, for example, in some cases, you don't necessarily need to know or understand what the black box is at the end of the day, if all you want is the patient, for example, to move the robotic arm with invasive technology, do you really need to understand everything? In a research perspective, yes. In practical context, maybe yes, maybe no. I'm not that sure. So I think it depends on we need to evolve in parallel in understanding the black box, but also performance and understanding what is happening. I think that the problem is so obvious that there is a lot of PhD students, a lot of researchers now tackling it. So I'm really excited for like in 2, 3, 4 years from now, I think we're going to learn a lot. But right now we're all kind of like in that black box. I'm going to let Tonio, because I think that he wants to reply to what I just said. But just quickly, just so we know in the audience, who has done deep learning for brain data, just by show of hands, just so. Okay. All right, thanks.
Yeah, finally we can disagree. So, because I think if you imagine controlling a robotic arm, and you would really have a person doing that, and now let's say this person would, it would be sad, of course, but would, let's say, shoot another person, and then this person would maybe say, well, I didn't want to do it. Maybe I thought about it, but I really didn't want to do it. And it was just the classifier that didn't work correctly. So I think, I mean, this is maybe an extreme example, but I think that in many situations, it's really important to be able to understand the process even for legal and ethical concerns. But also to make it a viable tool for us in neuroscience, I think it's a really important aspect. And I agree that maybe there are some applications where you can live with a black box, like maybe BCIs for gaming applications. There I can imagine that it would be completely acceptable. And but even there, if you imagine that, I think this was a really good point at the last BCI meeting in Asilomar by Jonathan Walpole, if I remember correctly, who said we have to be aware of the fact that we are now creating an efferent pathway connecting the brain to the environment in a way that didn't exist for our whole evolution history. So the brain is just has evolved to be connected to our environment via our muscle system, and so I really good. Yeah, I think it's a really interesting thing to think about. What can it potentially mean to create this this output channel that could be potentially unnatural and might induce adaptive changes that are maybe not necessarily good.
I guess I can't speak to the legal system with a jury in all the countries represented here, but in the United States, if I were in front of a jury and they had to understand the inner workings of a multi-headed LSTM attention-based transformer network, I would be hopeless. And I think we routinely accept the fact that we don't have a clue what's happening inside our skull, but it's the same kinds of processes that could go awry in some way, and you know, let me shoot someone and I'll just say, well, you know, I was temporarily insane, and the jury just has to decide. I think your example is a little bit too science fiction-y for my taste.
No fighting. Okay, so let's move on. Tonio already nicely mentioned that actually BCI can be used to kind of expand our interaction with the environment. So let's talk about VR and AR, which is in our title. And I would like to ask everyone now one by one, if you can shortly tell if you have any experience already with VR and BCI, and if not, what would you like to do with these technologies?
Thank you. So actually, do you have an experience? Yes. So actually, the title of my PhD was using BCI for virtual reality. So I do have some experience of that. But that was, I defended 10 years ago, maybe more than that now. Yes, 11 nearly. And at that time, we were really hopeful that BCI could be the next interaction device to control virtual reality environment in a more natural way, blah, blah, blah. Now I don't think that anymore, and probably most people don't think that anymore. We were thinking that BCI could be really the new gamepad, and that could be nicer, more immersive, etc. So we developed a number of virtual reality applications controlled by BCI. Obviously, it was a hell for the users. It was super slow. It was not reliable. 10 years after, it will still be very slow and still be very unreliable, maybe a little bit less, but not that much less. So I'm not really working on that anymore, at least not with the objective of controlling virtual reality environment using brain-computer interfaces. But we still work on augmented reality and virtual reality for some other types of applications. For instance, we are working with some companies in Bordeaux area in France in which we use BCI and some other physiological signals for neuroergonomics, so to have objective measures of the ergonomic qualities of virtual environments based on brain signals. For instance, we measure mental workload and we can compare different interaction techniques or interaction device in VR based on brain activity to see which one are more easy to use or not, when or where they are more difficult to use or more easy to use. And also we use augmented reality for education. So we design some tools in which we use AR to actually show to people what's going on in the brain activity. So we have developed, for instance, one system that we call the mind mirror, in which people look at themselves in a mirror, and there's an overlay that displays a brain with real-time activity. It's actually their own real-time activity, so they can show what's going on in the brain when they do different tasks. So it's purely for educational purposes, but that could be an interesting and sexy way of doing that. But
yeah, I'm coming from a vision lab, so we do a lot of VR to analyze different cognitive and low-level, high-level function with vision. So we have a cave, HoloLens, Magic Leap. We have like a lot of different toys, and we've tried obviously to do some BCI, EEG stuff in it. VR is not there yet. BCI is not there yet. So combining both of them is interesting from a research standpoint, but not necessarily from an application and in real life just yet. But one of the first, I personally believe that it's very important because it's a natural headset that like BCI and EEG from like in different out of the lab. It's just a natural headset that you're gonna wear, so there will be sensors, obviously, and then we'll do multimodal from EMG, EOG, EEG. You'll combine that, and you'll have a lot of insights, whether it's for active, passive, reactive BCI in it. So that will be a new input. Your brain will be a new remote controller in the VR environment. So that's I think that we all agree, or at least I agree with that, that's going to be the future. So it's very exciting for that. One of the first cases that I think that at scale will reach VR in people's home will be neuromarketing. I think that data analytics, sadly, will be one of the first case where we'll leverage brain data in people's home, because that data is really valuable and there is a huge market for it. So I think that there will be a lot of company jumping on that. In terms of the control that everybody dreams about, controlling VR for active BCI, I'm not too sure about that in the near future, but definitely passive and reactive to just get data and modulate the game or the application for education or in different cases. I think that has a lot of value in the near future.
I really don't have much experience with either VR or AR in my research setting, except that we are interested in developing bidirectional BCIs. In addition to recording from the brain, we stimulate the brain to try to put some metasensory information back in, and I know that is tremendously difficult. So I think the only comment I would make is I am highly skeptical of any interface to an intact individual that people are going to claim can augment what we're able to do through our natural senses. So I think augmented reality in which we project images directly onto our retina or looking at screens are fine. I think those are interesting. But the notion that we would make an interface to the visual cortex and somehow do better than what we've evolved in the last 10 million years to do is fanciful for at least the next century.
So,
even with highly invasive arrays.
So, maybe similar to what you asked before, I would be interested to, so again, in the audience, so who has tried out like one of these now commercial Oculus Rift or Vive VR sets? Oh, okay, that less people who have as for deep learning. Wow. So because then I tried out the Oculus Rift, I think now pretty much after it was came out, and I must say for me this I didn't expect like so much, but so already the demo of it was for me like one of the absolute like wow moments ever. So I don't know with the new version if they still have this demo, but there it starts really like just like a cartoonish environment, and okay, it's super three-dimensional and impressive, and you think, okay, wow, okay, that's really cool, but also not so, you're not blown away. And then there's the next, it's small demos, and the next one is you're in like a corridor, like a school, and then you hear like heavy footsteps, and then like a huge dinosaur comes around the corner and walks up to you and somehow roars into your face. And this was like such, this came so unexpected, and this was really, it was impossible not to feel really frightened, I must say. So therefore, I think that we are maybe not on the basic visual level, but even there, I think one can create situations which are hard to do otherwise. But from the emotional impact, at least from my personal experience, and even not to talk about like sophisticated games, which really are very impressive. So I think that from what you can do on an like emotional level, I really can only recommend to try it out. So I found it super impressive, and so therefore, from my personal experience, I think if you talk about applications in like in psychiatry, systematic exposure to threatening situations which would otherwise be hard to do. So how would you do a systematic these sensitive, like a training if someone has fear of flying, so it would be very costly to do that. So in there you can do it more easily. And so there are many good ideas, and I think so. I really believe that it has huge medical potential, and so I find it a really exciting technology.
To be clear, I agree entirely with what you just said, but that's an interface through your retina, not through electrodes in your visual cortex. That's the distinction I was making.
Oh, okay. So you are already, this will be the matrix.
Yeah. The matrix isn't going to happen anytime soon.
Yeah, no, then we are on the same page. Yeah, I think this will take a little while.
Yeah, my point is, you know, we talk about trying to develop high bandwidth direct access to our brains, but we've got incredibly fast bandwidth through our visual cortex by speaking, very fast output and so forth. We're not going to equal those anytime soon.
Yes, we recently built a so-called MOBI lab in Berlin. It's a mobile brain body imaging lab where we have 160 square meters where you could walk around while you wear VR goggles. So you are really, your motions are tracked by multiple cameras so that you see in the virtual environment also your own body and your movement of your hands and arms. And this really gives a high immersion. So from that perspective, it's not only that you could sit there and look around and see something happening around you or walk with a button press through that virtual world, but you really can walk, of course, in limitations by 160 square meters, but you can really walk in an open space and experience the virtual environment in a way which is quite natural. That is one thing which increases immersion. But then we can also record a high density EEG while you do that. So we have 168 channels of EEG while you walk through that environment. And then you can interpret the brain states immediately when they are changing. So you can set up a BCI, and you are interacting with a virtual environment, an object in the virtual space, and you see the reactions in the brain, and you can then modify that environment or that object. So there might be a blue ball, you don't like it, it turns red, and you like it. And this is something where I see a high potential in science, but also maybe for future real-world applications or virtual world applications, so that you could set up virtual environments which are highly adaptive to your cognitive interpretation. And then you can reinterpret the brain responses that you understand how the environment was affecting your state. And so closing the loop in a virtual environment is much more powerful because you can change the world in any degree. When I'm sitting in front of a desktop which is made out of wood and metal and whatever, I cannot change that physical object immediately. But in a virtual environment, I can do that, and I can see how the brain reacts on that. And that gives a closed loop immersion, if you want to say it like that, which is not investigated yet. So we can magically adapt the world to the intentions of the brain, to the things the brain want. And this is nothing we don't have much experience with that. We just have that now available, and we want to explore that and see what is the effect of that, what can we do with that, what can we learn from that. And I think there's a huge potential to learn more about the human neuroscience in a more natural environment. So not sitting on a chair, moving just one finger, but really moving around and see how the brain reacts to the virtual environment.
Trying to inject some controversy again, I have a question. You referred to seeing how the brain reacts to a desk that suddenly changes. Mm-hmm. But if I understand it correctly, you guys are more or less happy recognizing whether you've squeezed your left hand or your right hand.
No, so I'm not speaking...
A little more than that.
No,
what can you really tell me about the brain?
I'm not speaking about anything like direct control, so that you... it's not that I voluntarily squeeze or think about squeezing my left hand and influence the world, but that I see something like surprise or an error response or a high workload or anything.
But can't you tell that by looking at someone's face just as well?
No, not as well. You know, I think my mimicry is different when I'm sitting here talking to you, or when I have the same thoughts sitting in my own lab and on my own office. I might not have the same mimicry. And also, it's much easier to manipulate my mimicry. I might now look very angry, even though I'm not, and my brain state might be very different. So I think we can get, and also there might be some things which are not aware, which we are not aware of ourselves, you know, of our mind, and there's a different time aspect. So of course, I fully agree. If you can get the information from a camera, use the camera. Don't use EEG. And I don't say it's exclusive, but we did recently, so one more addition to that, we did a study where people in the US, where people played a game and they were supposed to bluff in the game. And in that case, you really do anything that your opponent doesn't see how you feel, but we can read it out very accurately with the BCI. So, and that is an example, which is of course might have ethical implications as well, but it shows that we can read much more information from the EEG than we think, and much more reliable. But it should be, of course, a combination of any information we have available, a camera, sound, context information about the environment or whatever. But I'm pretty much sure that the brain will provide information we cannot read out by other measures.
Okay, first to address your thing, you said that matrix is not happening anytime soon. Many people believe that we are in a matrix right now. So that's also a controversial thing. But now going directly to your topic about a combination of virtual reality and BCI. So probably some of you also have now, there is a Journal of Physiology special edition dedicated to exactly this thing. We have the paper with Barcelona team, who are the pioneers, of course, of virtual reality with Slater. So there what we did, we used basically brain-computer interface together with Oculus Rift, and to see to what extent sense of agency emerges when you have SSVP versus motor imagery and versus real movements. And so that's actually was one of the studies where we really combined BCI and virtual reality, because the hand which has been moved in virtual space was completely driven by the signals from the brain. And interestingly, although SSVP had a much better accuracy, people naturally had better sense of agency and responsibility for movements for, of course, motor imagery. So another example which I think is very useful for using virtual reality is a little bit to tweak, for instance, expectations for, let's say, proprioceptive feedback and visual feedback. For instance, when you are touching an object, you can, in virtual reality, make a delay between actually what you see and the sense of touch. And this actually allows you very naturally to study, again, sense of agency. And this is quite a powerful approach, actually. Not to mention rubber hand illusion, which is devastating in virtual reality. You really feel your hand is hammered. And of course, now speaking of augmented reality, so in a clinic in Leipzig, which is we have in collaboration with Max Planck, we have KinArm system. Probably some of you know, Mikhail definitely knows. So this is an exoskeleton, but it's designed for investigation of upper limb movements. So in there you have this very nice augmented reality where you can stimulate and simulate diverse movements. You can actually also create different force fields. And there we use it for recovery and rehabilitation for stroke patients. It works very well, and it tracks trajectories of the movement very nicely. So now our next step would be to combine it with EEG to see to what extent we can predict successful movements on the basis of EEG, which was just preceding it. And then maybe through neurofeedback, augment it so that there would be a better neuronal state for movement performance. The same thing goes actually for freezing of gait in Parkinson patients. The people who are freezing right in front of the door, we have it with virtual reality where we simulate the person is walking on a treadmill, and then we have this door appearing, and then we can investigate also the kind of neuronal precursors for this.
Yeah, I just have to reply here. I think a little bit because you said that we are more or less happy if we can get out if you're moving your right hand or your left hand from non-invasive data, and I know you're looking at this cool spiking activity. And but now I want to ask you something. So imagine you're in a plane, and you get the possibility to monitor whether the pilot is falling asleep, which could be bad for you. And now I would offer you, you can record 10,000 of your signal units, or let's say 1,000 channels of ECOG, or 20 channels of EEG. So which one would you pick?
I put a camera looking at his eyes.
No. That's not an option now. You were referring to decodability from neural signals. So which one would you pick? Any number. So 10,000 single neurons, 200 channels ECOG, 20 channels non-invasive EEG to say whether your pilot is asleep or not. I can tell you what any clinician would pick, which is the 20 channels of EEG, because
Well, but I think it's relevant to know. You've given me the whole problem, and so I would say, sure, if I want to know whether he's asleep or not, I think there are even easier methods in ECOG, which I would use. I'd use a camera if I can. I don't think there's need to put EEG or ECOG on the pilot for that problem.
But what I wanted to somehow say with that is somehow the question of what you can do with. So I want to make an argument also for non-invasive EEG, because I think it's and I think it's not by chance that actually in our department, if you want to do sleep staging, and even with patients who have more than 100 of intracranial EEG channels, the clinicians always want like 20 additional non-invasive channels, because it's just so much clearer to do sleep staging and to see these changes in global dynamics. And I think this is not like a curiosity, but I think it's just a hallmark of such highly nonlinear systems that you get somehow interesting and meaningful dynamics on multiple scales, not only in time, as you've very nicely shown in your presentation, but also in space. And therefore, I think there's the non-invasive EEG is really, it's not an inferior kind of ECOG, and ECOG is not an inferior type of intracortical recordings, but it's just different related, but also in itself interesting scales. And so for certain problems like sleep staging, or maybe also passive BCI applications in VR situations, I think it's really fundamentally you can imagine situations where these global scales are really useful.
I agree entirely, and I think your example of the pilot falling asleep was the wrong example for your question. But I found myself in a similar situation. We're studying the area 2 in the somatosensory system, and we'd like to know what kind of map is represented on that part of cortex. We know a lot about visual cortex and the way the retinal signals are laid on the cortex. We really don't know much about area 2, and the little tiny Utah arrays that we put in are too small to see the spatial scale that we'd like to. So, in fact, we would like to put on some high-density, large ECOG grids for that problem.
Great, wonderful.
Well, I think the example you may think of is if I want to know something with a large spatial scale, I'm not going to stick 50 Utah arrays in to try to cover the brain. That's clear. So if I do want to see the dynamics of large cortical areas interacting, then this is the only suitable approach.
Okay, wonderful. Do we have any questions from the audience? Yes, sure.
Hello. Yeah, thank you. Actually, I wanted to make a little comment that the previous question was kind of loaded one, because the pilot problem is obviously like simpler for the Utah array data. And I mean, that was a loaded question to ask if the pilot sleeping problem should be solved with an EEG or the Utah array. Yeah. I mean, and that's not the point. The first point is that it's obviously very sad to hear that we are really far from metrics. And the question is, according to the bidirectional BCI, so the problem to be addressed as all the presentation that we heard, that the Utah array, first of all, degrades severely. And in terms of bidirectional, I mean, in terms of stimulation, how do we address that? even the so like popular Elon Musk's reported results, it's 85% of stable electrodes staying 2 months after the implantation. So the UTRA, I believe it's really even worse than that.
We routinely have arrays that last 2 years.
But since, I mean, like even if we list 10% of like the electrodes, how do we go backwards? How do we stimulate the neurons? So that's the question.
So a number of responses to that. One is the basic problem is that you're absolutely correct. We need better interfaces beyond the Utah array, invasive interfaces, because of exactly the problem you raise. I think the lifespan of the Utah array is actually better than certainly what you described, and it has gotten better in the last 5 years after they had some quality problems, which I think they've addressed. But the problem is bigger for recording than it is for stimulation, because you can turn up the current and stimulate more aggressively and continue to get effects for years. Unless wires actually break, then of course you can't.
Well, then there is a point about the stimulation itself. Since we don't, getting the data it sounds really easy. So we can decode something happening in the mind, not sure about what's exactly happening. But about the stimulation, I don't remember who was reporting the example of feeling the invisible line on the screen. I believe that was work for the Mikhail Lebedev. He's not here right now. Oh, and somebody also reported that. And so I believe when we stimulate something by the UTRA, we don't like get the real feel of touch. We just get some feeling. And so this doesn't sound like a really close step to the metrics.
I think there are a number of reasons for that. I think the stimulation, I implied that we don't have as much problem over time stimulating through the array than we do from recording, but the stimulation problem is much more difficult. The sensory encoding problem is much more difficult than the motor decoding, because we can record from single neurons if we want to, and we can make either simple linear maps or very complicated convolutional neural networks and decode a remarkable amount of information from 100 or 1,000 neurons. It's really quite impressive. We can do that from sensory areas as well, and we may understand well how these areas encode vision or hearing, or in my case, touch and proprioception. But even if I have a map from from sensations to neural activity and know which neurons I'd like to activate, we have no tools for activating individual neurons electrically to essentially play that signal back into those neurons. We're activating hundreds or thousands of them simultaneously, or in ECOG, tens of thousands of them. And each of these neurons carries a different piece of information, so if we turn them on all at the same time, there's no way it's going to work. And if we use tiny enough currents that we really do activate only 1 or 2 neurons, then it's going to be a vanishingly tiny little sensation that's no good either.
Do you have a vision how to solve that problem?
The only way I can see to solve it is by getting electrodes that interface to many, many more neurons, tens of thousands, hundreds of thousands of neurons. But how to do that, I don't know. Optical methods, perhaps.
Okay.
I guess I'll follow more or less this question. It's about eye prosthetics like Argus, because there are like nerve ones, and as I know there are cortical ones. So the question is, do you think that such eye prosthetics will ever evolve to the point when it's almost identical to the natural vision at some point in time?
No chance.
No chance, yes. Okay.
Hello. What do you think about?
I mean, you ask if it's imaginable at any point of time, like
A millennium.
right. So I think I don't see a fundamental physical limit that or reason that would prohibit something like this to realized, but yeah, I think this would be probably a time scale that I could imagine. Yeah.
Hello. What do you think about idea to create with VR virtual environment where human can easy train to use BCI, training environment. And after it, use skills from virtual environment to use BCI in real life.
So there are actually some work already we started to do that. So notably in Spain, I know there are some colleagues who first compare traditional training in BCI using the classical bar feedback, so to more like gaming control in VR, and they observe that usually people get better with VR, probably because it's just more motivating and less boring than the classical bar feedback that we use. And so it's the University of Malaga who did that, and they also have some training programs where they do what you suggest. So they first train people to control a BCI in VR, then to control a small robot in VR, then they move to a system in which they control a small robot in real life, and then they move on to wheelchair control using the real BCI. So it's a progressive training. So I think it can be useful. It's not clear yet whether you actually need something as complex as VR to do that. So maybe something just more motivating and more diverse training environment using simpler 2D screens could be enough. I don't know yet. But definitely it could be useful to have something a bit more structured, a bit more motivating, a bit more engaging to help for the training.
Okay, wonderful. Sure.
Let me go back to your question once more. I think your example was to stimulate the retina. And I think as we get further from the brain, closer to the periphery, the problem does become easier because we get to go through many more processing steps along the way, because the peripheral codes tend to be simpler to understand and probably to interface to. But the dilemma is that you get farther to the periphery, there are fewer patients who can benefit from it. So my initial reaction was probably more pessimistic than necessary, but it's a very, very difficult problem.
But do you think the brain cannot evolve? Just you're not trying to think that you won't try to code the information. You're just feeding the information into the cortex and let the brain just figure out what is the picture. Do you think that even this isn't possible if we have, I don't know, like a million electrodes array and we're just feeding the picture and we're hoping that brain will figure it out? Or you think even this isn't possible?
I think those are interesting questions. We're pursuing some of them in my own research work. I think if you put noise into the brain is not going to figure it out. But if you're maybe close to reality, certainly you can improve. Cochlear implant is a good example of that. My understanding is it begins sounding like noise, and within weeks or months, you begin to perceive speech. And there are differences whether it's implanted in a very young child or an adult with the respect to undertake that plasticity.
Okay, so since we have only 5 minutes left, I would like to move to the final part of our panel. So basically, day-to-day use of BCI or healthcare. If each of you could make very short comment, what do you envision in the short term, or what would you like to use BCI for? Healthcare, day-to-day, sleep, prediction, microsleeps, and so on. Like 1 minute each.
1 minute each. Okay. Tricky question. I would go for maybe motor and cognitive rehabilitation. Maybe that's an area in which BCI could be hopefully useful. So definitely it has some impact. It's not 100% clear yet whether it's better than some other rehabilitation. So I think Sergio actually gave a nice example of that yesterday in his talk. So, but that's a promising area. So I would bet on that for the moment, but probably in a few years that would be different. I don't know.
I'm going to go more on the consumer-facing side, less of the medical side. For my example, I would like BCI for more productive work. For example, with headphones, things like that. When I'm working on my computer, just having like passive recording, knowing when I'm more focused, having information over time, blocking notification, that kind of thing. I know that a lot of the companies like Microsoft have a lot of patent in that field, so we should see that coming. I think it's more of a question of a form factor also, and adding the value and application with your desktop, but that would be for me kind of like an easy path for BCI and consumer-facing fashion.
I think I'd have to stick with the work that I'm involved in. I'm not sure, it's certainly what I'd like to see. I'm not sure just how soon it will be, but the idea that we can record from the brain and effect movement of the patient's own limbs is something that I think within the next decade could be feasible for restoring motility to a spinal cord injured patient. And there's a fair bit of evidence, back to the plasticity theme, that by doing that, we can augment the recovery, perhaps of a spinal cord injured patient, but there may also be applications to stroke patients, which is a much, much larger patient population that could benefit from that.
Yeah, so the question was what we really think would be
realistic,
possible. Yeah, I must say I'm not sure. I don't know. So I'm, for me personally, still looking for the application that will really make it into something that's so useful that it's not just like something that you would use maybe once, but that even or either in a clinical context or in a consumer context would really make it into like either like daily practice or something like that. So I'm still searching. Good to have such occasions like this to do that, yeah.
So I personally think that we will interact with artificial intelligence much more in near future, so that specifically in the form of robots. So we will have robots teaching our children, we will have robots taking care of our elderly people. That might be away 10 years or even longer, but we are aiming at that, we are moving towards that. And in that case, if our children are taught by a robotic tutor or something, I want to see some empathy in that robot, some understanding of the people, or specifically also in elderly care. Does the person want to be supported or not to be supported? And therefore, we need to create some understanding of humans in robots, in artificial intelligence, and we can use a lot of, we should and could use a lot of information for that. But specifically, the momentary information about the cognitive affective state of the user is hard to process in any or assess in any other way than by using a BCI. And this is where I'm aiming at, using a passive BCI to inform an artificial agent about the current state of a person so that the agent can interact in a better, more safe, more empathic way with the user.
So your question was near future on a daily basis. So I would probably spend 5 minutes a day in the morning upregulating my activity in left dorsolateral prefrontal cortex, attenuating alpha at F3. So I guess it could be a start for a better mood during the day.
Okay, thank you very much. Any comment from the audience or question? Okay, sure.
Здравствуйте. Спасибо. Я хочу вас спросить, раз вы говорили о нейрокомпьютерном интерфейсе, об искусственном интеллекте и дальнейших технологиях. Вопрос о будущем компьютерного интерфейса. Как вы думаете, может ли искусственный интеллект и компьютерный интерфейс поглотить человека? То есть человечество будет поглощено технологиями или же нет?
Will artificial intelligence capture humans? Take over?
Потому что я могу сказать, откуда у меня такой вопрос. Я прочитала книгу Дэна Брауна «Происхождение», где он описывает о том, что появился искусственный интеллект Уинстон, суперкомпьютер, который очень помогал владельцу в настоящей жизни. Но в результате этот же компьютер, судя по всему, спрогнозировал смерть своего хозяина.
So this computer was very helpful, but then it predicted the death of its owner.
Нет ли у нас сейчас таких же рисков в применении искусственного интеллекта и компьютерного интерфейса?
Do we have such risks nowadays?
I was a big fan of Isaac Asimov and the 3 laws of robotics. I'm not sure those will solve the problem, but I think the tremendous power of artificial intelligence and the way that it's wired into everything we do, I think it's a significant possibility.
I mean, so you're talking about the Terminator Skynet scenario, and I think, I think it's something that could happen within the next 10 to 20 years. It's it's something that could be really happening. Yes, I think so.
But please don't worry today.
So I'm definitely sure that something like that can happen. So that we have a superintelligence within our lifetime is quite likely. So that with the progress we have right now, not only in the field of BCI, or specifically not in the field of BCI, we will have a superintelligence, let's say in 20 years. But the question is, how do we create that a superintelligence? And I think my opinion would be, I want to create it as close as possible to our own intelligence, to how we think, how we are, to the human intelligence. And there, we can argue about that, and I agree to that. But my personal opinion, we don't have time to explain that too much. No, but that we can interact with the computer, that we understand each other in a better way. And there BCIs can help. So we can argue about that, whether that's a good idea, but in my opinion, we can connect our mind to the superintelligence in a better way if we use BCIs, and that might be helpful to have a coexistence. But that's a difficult topic, yeah.
15 seconds.
Yeah, I would just say don't worry too much. Elon Musk will save us all. So he's working on that problem as we speak, so we're good.
There is this field of consciousness, and there are some theories of consciousness. I think the most advanced is this integrated theory. So can you speculate if BCI field could connect to the studies of consciousness and may help it somehow or make it worse?
Short comment. 10 seconds.
Well, I don't know in 10 seconds, but yeah, I guess probably because there are some nice experiments actually by the Berlin group actually in which they try to see, because in brain signals in EEG you can predict, you can see whether a movement is going to happen before it actually happens. So they can actually ask people to do a task and to do a gesture and actually detect in advance that they will do this gesture and change the task between the moment they detect the gesture and the actual gesture. So they could see whether you could, how far before you can cancel a movement consciously or not actually. And so this is an example of in which BCI could be a very useful tool for research, because you can play with actually what people consciously perceive or do or not, and see how far away is consciousness, I guess, in the signals. Maybe, I don't know, it's a guess, but maybe that could be a useful tool to manipulate what people do consciously or not.
Okay, thank you very much. We have to finish because lunch is waiting, and amazingly we are on time. I would like to thank all the wonderful our panelists. Thank you for doing my job so easy. I didn't have to do anything. Thank you to the audience. Thank you for the great questions. Thank you, guys.